Hello and welcome to this video. In this video we're going to be looking at the idea of phases and interference with waves. So we already have our four properties of our wavelength, frequency, time period and amplitude. Those were all very GCSE type properties. We're now going to go a little bit further and introduce this idea of phase. And then use this idea of phase to explain how two waves will interfere with each other depending on their phase. So let's go back to this diagram of a transverse wave. Okay, so we said transverse waves were very similar to sine waves. So let's just have a look at something like this. Now, let me actually do it a larger scale, since we're going to have to do a little bit of annotating here. Okay, so now what we have here is a sine wave. So I'm just going to actually make this sine of x and x here. Now, what we would already know about sine waves, or what you should already know from GCSE, is how we would label this sine wave if we were looking at this in degrees. Okay, so if we're looking at it in degrees, this is 0 degrees. When it reaches a maximum of 1, that's at 90 degrees. It comes back to 0 at 180 degrees. It goes to a minimum of -1 at 270 degrees. And it reaches back to 0 at 360 degrees. And that is one sine wave. Now, the whole idea of degrees was based on the time it takes to get around the sun. We said it was about 360, so they roughly guesstimated that if we're doing circular orbits around the sun, then that's going to take 360 degrees, and so that's how we got that degree system. We don't actually use the degree system anymore, because when we get to high level maths, we see that the degrees starts to break down and no longer makes much sense. So instead of degrees, we're going to introduce a new way of looking at angles called radians. Okay, so this is basically a measure of an angle. Okay, so it's just like it's a unit of an angle basically. So instead of saying degrees, we're just going to say radians. So it's a measure of angle. Okay, now the whole idea of radians is that they're specific based off of pi. Okay, so they're defined by circles, which mean that they're actually much better than degrees. So what we say is that there are 2 pi radians in, so this would be x in radians, so we call them rad. There are 2 pi in 360, which means there are pi in 180. We still have 0 here. This is going to be half of pi, and this is going to be 3/2 of pi. Okay, now whenever we describe phase, we always use the radian system, because it's much more useful to be able to describe the radian system than it is to describe the degree system. Okay, for those of you doing maths, you'll come to look at the radian system anyway, so hopefully by the end of the AS at least, you'll be really comfortable with radians. For those of you who aren't doing maths, I would say try and honestly just memorize the idea that 2 pi radians is 360 degrees, and you can use this to convert between the two. This means that if we want to convert from, so if we wanted to go from radians to degrees, just in case you want to do this, what you would do is multiply by 180 over pi. And if you wanted to go from degrees to radians, you would multiply by pi over 180. Okay, so this is just extra information if you prefer to work in degrees, but I would say always try and remain in radians as best you can. Okay, now what phase means is it's essentially a measure of the displacement between two points on a wave, but it can also be the displacement between two waves that are both moving individually in space. So let's first look at what the phase difference would be between 2 points. So if I chose this initial starting point, and then this point here, and call this point A and this point B, I would say that A and B are pi out of phase. They have a phase difference of pi. Okay, this term out of phase, we will see pop up a lot. We're also going to introduce some specific phase differences known as in phase and in anti-phase, and then the rest of them just relate to being out of phase. But in general, we can see that this is pi difference because they're half a wavelength across. If I had a point here that I'm going to label point C, then we would say A and C are pi over 2 out of phase, because they just have that difference between them of pi over 2 between 0 and pi over 2. We would also say that B and C are also pi over 2 out of phase. If I had A and then I had D, that would be 3 over 2. If I had an E here, they would be 2 pi. So you can always tell the difference between them. Sometimes you might have something that's here, that's B, that would be like pi over 4, halfway point. A and let me be consistent, F, so A and F would be pi over 4, so would F and C, but B and F would be 3 pi over 4 apart, because they'd be pi over 2 plus that extra quarter. Okay, so this is between points on an individual wave. If you wanted to tell if something is in phase or in anti-phase, what we generally say, and this works for both just the points on a wave and two waves in general. I'm going to get rid of these conversions over here for a second. So if things are in phase, it means that they are doing the same thing. Okay, so for example, this point A here, the next thing that it's going to do is move downwards if this wave is moving in this direction. And so if that's going to move downwards, the endpoint E here is also going to move downwards. We would say A and E are in phase with each other because they're doing exactly the same thing, and they will follow the exact same thing for all the time of propagation. So A and E will always be performing the exact same movements. Okay. And for that reason, we say that we can have, if you're in phase, it means you're either 0 pi apart, meaning you're literally on top of each other. You're 2 pi apart. Then we could imagine we had a whole extra wave. We could be 4 pi. We could be 6 pi. So basically, any even value of pi means that you're in phase because you're performing the exact same movements at all times. Okay. The opposite of in phase is anti-phase. Okay, so this is when you're doing the exact opposite of all of those movements. So for example, A is going to move downwards next, but B is going to move upwards. And these 2 points, if you were to have a mirror image of what they're going to do at all points, they always perform the opposite motion. So where this is going to move up, it's going to get to the top and then start moving down. This is going to move down, get to the bottom, and then start moving up. So they're always opposites. And that's because they are pi apart. So any odd values of pi, and this will keep going on for both of these, but any even values of pi, any even multiples of pi are in phase. Any odd values of pi are in anti-phase. Anything in between these, because we could have like pi over 2 out of phase, or 3 pi over 2 out of phase, or any of like multiples of that, pi over 6, pi over 9, whatever you want. That's what we just refer to as out of phase. Okay, so this is basically anything else. And it's out of phase because while they may do the same motion at some points, they're not always following each other, but they're also not always the opposite. So if we take, for example, A and C, the next thing that they're both going to do is move down. But when this moves down and gets to the bottom, this is going to move down and get to halfway. And when it's at halfway, when this one flips to start moving up again, this one is going to keep moving down. So they're out of phase because they're not exactly following the same motion. they will at some points follow the same motion, and at other points they won't follow the same motion. Okay, so this is a very key idea for you to wrap your head around. This idea of what an in-phase and anti-phase means. We can also apply these exact same values to looking at if we had two separate waves, how would they be, how would their phase differences look? And the way we would look at that is, let me just start afresh down here. Let's say I had a wave, I'm going to make this almost like a start line. This wave starts like this, where this is its equilibrium line, but this wave down here starts like this. Okay, I'm trying to do this as accurately as possible, where this is the equilibrium line. Okay, so this starts at 0, essentially this is a sine curve, whereas this starts as 1, so this is a cosine curve. And if we were to map down each of its points, we would say that these two things, because we start at this point, and this point here is at this point here, so we're starting at 0, that point there maps onto when this is at 0, so this is pi over 2, this point here is pi, this is kind of very badly drawn now, because this point here where this is a minimum should go to the next point along. So let me just try and retrace this cosine here. So let me just see if I can map it out. So this is going to be 3 pi over 2, and this is going to be 2 pi. Okay, so it comes down at pi over 2, down to a minimum at pi, back up to the middle at 3 pi over 2, back up at 2 pi, and it will continue to do this for the rest of it. Let's just focus on this section here. This point here corresponds to the highest point on there, and those are pi over 2 apart. Okay, so these are pi over 2 out of phase, these two waves. Okay, and it's as simple as that. You just need to find out, try and map a single point onto the second, onto each of them, and you'll be able to figure out their phase difference. Let's go with something a little bit more common. So this isn't too common. Let's try one where we have 0, and let's have a sine wave to begin with. So this is my sine wave. Let me go down so I can start fresh again. This is my sine wave with some equilibrium line. And then I'm also going to have a little bit further down a negative sign. So it's still a sine wave, but it follows the opposite trend. Okay, so where this is a maximum, this is a minimum, where this is a maximum, this is a minimum, and vice versa. Okay, so this one is drawn much better, and we would say that this point here is the next thing it's going to do is move up, so that relates to this point here, because the next thing that one's going to do is move up. We can't relate it to this point because this point is next going to move down, so they don't correspond to be identical points. Okay, so if this point here corresponds to this point here, that means that these things are pi out of phase, which we would refer to as just being in antiphase. Okay, now we could also have something, so let's say we had, let's say we start with the sine wave again, and then the second one we had was also a sine wave, so it was an exact mirror of these. This point here does relate to this point here, so there's 0 out of phase because the next thing they're both going to do is move down, so there's 0 out of phase, which means they're exactly in phase. So this is how we're going to approach this idea of looking at the phase difference between things. I'm actually going to split this video in half and now do a separate video on the interference that these things will have based off of these phase differences, because I don't want to have a too large of a video. So hopefully all of this phase stuff makes sense. It is a little bit of a tricky concept to wrap your head around at first. It might take a few watches of this video before you can just be able to spot the phase differences. I would say try just drawing out two waves and then seeing how those things would have differences, or draw out a single wave and pick 2 points on the wave and try and calculate their phase difference. You can always do that as a practice to make sure you can calculate these phase differences. Hopefully all this phase stuff does make sense, and thank you for watching.